share my screen. You can see should go by the time of the font, so it would be just quickly. Okay. Just wait 1 minute until people come in. Okay, so now it's 3 o'clock. So thank you everybody for coming back to the online SPICE-SPIN+X seminars that I lead here together with Libor Schmeichel, Angela Wittmann, Karen Associated now in Duisburg, and also Alexander Muck, that I don't have here, but I should be here, that we do in collaboration with the Collaborative Research Center SPIN+X, led by Matthias Chloe here in Mainz, and in Kaiserslautern by Martina Schliemann and Burkhard Hillebrand. As you all know, this is a webinar format, so you'll see the panelist and the speaker. Please raise your hand or write in the chat the questions, and I will promote you afterwards to the panel to ask the questions directly to the speaker, or if you cannot speak, I will ask it for you. Please keep in mind of looking at the schedule, because we try to do it every few weeks, or depending on the overlap. Unfortunately, Felix von Open had to cancel for next week, but it will be rescheduled. But please keep that in mind. Today's speaker is famous enough, I can just say it's Dan. So by saying Dan, everybody knows that it's Dan Ralph in the field of magnetism. So it's that type of person. He's been in the field for a long time, leading particularly in spintronics and spin torques, and now Antiferromagnetic spintronics and spin transvector, and has many awards. But the one to highlight is the recent one is the James McGrory Prize for new materials, but he's also had the Sloan Baker Fellowships, the William Macmillan Award, and also one of the I like, because it's Research Corporation for the Department of Science, that I'm close to that organization, where he received the Research Innovation Award. So with this, I'm going to stop sharing and ask you, please, Dan, to go ahead and share your screen, and we will mute ourselves and give you all the bandwidth we can. Thank you. Perfect.
Okay.
Yep.
Actually, that's not where I wanted to start. Hold on just a second.
You probably want to go to the first slide.
Yeah.
It's okay.
Okay. That's better.
Perfect. Yeah. Perfect. Go ahead.
Okay, so I very much appreciate the chance to talk about the research in my group. I know some people will be watching live and some people will be watching delayed. And for those not watching live, I'm happy to have discussions. Just send me an email and I'm happy to answer questions or take your ideas. So my plan today is to talk about two essentially separate stories, both involving van der Waals magnets or antiferromagnets, and thinking about incorporating those into spintronic devices. But in terms of, they don't share much in physics, they mostly just share some fabrication techniques. So just to kind of set the stage, the first project I'll talk about what happens when you couple a topological insulator to a magnet. And what we found is if you do this using exfoliation and mechanical stacking, you can get much stronger exchange coupling between the topological surface state and the magnet compared to what's been seen before with MBE ground structures. We see at least half quantized anomalous Hall effects in the parity anomaly regime above 10 Kelvin, which is a factor of 100 higher temperature scale than what's been seen with MBE structures. And then the second project I'll talk about is sort of shifting gears, but talk about trying to understand and manipulate antiferromagnetic resonances in van der Waals antiferromagnets. So dealing with these in the frequency domain. And so we've built up some technology to use spin filter tunneling to detect these antiferromagnetic resonances and are beginning to be able to manipulate them and control them with spin orbit torque. But let's start with the project on the 3D topological insulators. Just to get everybody on the same page, to start with, is a bit of a review. 3D topological insulators are materials that are insulating the bulk, but have topologically protected surface states. At least if you arrange the Fermi levels so the Fermi levels in the bulk gap. And these topological surface states have Dirac dispersion that at least is semi-protected if you don't have these states interacting with the magnet. So I'll be interested in what happens when you do have these states interacting with the magnet. In that case, if they interact with a magnet with a perpendicular magnetic anisotropy, magnetization pointing out of the sample plane, that exchange interaction between the magnet and the topological surface state can open up a gap in the topological surface state, create Berry curvature associated with that gap. And if the Fermi level is positioned within that exchange gap, you can get an anomalous Hall effect, and it actually has a quantized value. If you just have a topological insulator flake with a magnet on one side, that quantized value is 1/2 the usual quantized value of the quantized Hall effect, e²/2h. And you see that if you have the Fermi level tuned to be within that exchange gap. So that's shown here schematically within this diagram. This isn't this state that's called parity anomaly state is different than what you normally think about with a quantized Hall effect in a large magnetic field, in that the longitudinal conductivity is not zero because you still have an ungapped surface state on the other side of the topological insulator. So that means because that longitudinal conductivity is zero, you don't have all that accurately quantized a Hall effect either, but this kind of gives you the idea about what's going on. And this effect has been seen both with magnetic dopants and some of the other quantized Hall effect systems. Things get even more interesting if you have magnetic layers on both sides of the topological insulator. If you have magnets on both sides with parallel orientation of magnetism pointing out of plane, the Hall conductivities on those two surfaces add, and you get a fully quantized, unit quantized Hall effect with a Hall conductivity of e²/h rather than e²/2h. And you also in this geometry do expect to have protected dissipationless chiral edge states on the sides of the topological insulator as well. If you take the same samples but orient the magnets opposite to each other, anti-parallel, in this case, the Hall conductivities on the two surfaces cancel. You get a total Hall conductivity of 0. And you also get what's been seen, a very high resistance, because in this situation, you quench the edge states. And so there's no particular way of getting longitudinal current through the sample. And with magnetically doped topological insulators at very low temperatures, they've seen magnetic resistance ratios of over 10 to the 5% at low temperature switching between these parallel and anti-parallel orientations. Okay, so this is all very nice physics, and it all has been observed starting a little over 10 years ago, starting with magnetically doped topological insulators. The first experiments only saw quantization below about 100 millikelvin or so. There's been a lot of hard work to improve that, and the later improvements, including modulation doping, have allowed these temperature scales to get up to about 4 Kelvin or so. And of course, there's also been a lot of other excitement about other types of quantized Hall effects within intrinsic topological antiferromagnets, Mori systems, and also observations of fractional quantum Hall effect. But all of those have been at temperatures below 2 Kelvin. Okay. So for a long time now, almost as long as the magnetic topological has been studied, there's been efforts to try to reach higher temperature scales by coupling topological insulators, 3D topological insulators, to using proximity coupling to an external magnet. And the logic here is that the magnetically doped topological insulators themselves all have fairly low Curie temperatures as magnets. So if you can couple to a higher temperature magnet, maybe you can get stronger interactions. And even though there's been a lot of effort about this, the results have been sort of disappointing so far. In the graphs here, I show what's been done with MBE-grown samples using materials very similar to the ones I'll be dealing with sort of mechanical stacking. sort of the 3D topological insulator in the bismuth selenide or bismuth telluride family, along with the van der Waals magnet chrome germanium telluride. Jason Petta's group in early work saw a little bit of anomalous Hall effect, but sort of resistance values below, well, on the order of 0.1 ohm. And the Takura group a little bit later, using samples with magnets on both sides of the 3D topological there, saw values of the Hall conductivity about 1/5 of the quantized value at 2 Kelvin. As far as I'm aware, there's only been one report of a well-quantized Hall effect in an MBE-grown proximity structure in which you have a separate magnet and a 3D topological insulator in a somewhat unusual materials combination below about 100 millikelvin. Sorry. So why is this difficult? Well, this picture illustrates some of the difficulty, and I'm not saying this picture is the best possible to do, but this was a nice study from Yuri Suzuki's group, and Nitin Samarth is a collaborator, really trying to understand what goes on at the interface of these kinds of samples. In this case, between an insulating ferrite material, magnesium aluminum ferrite, and bismuth selenide. And basically, it's very hard to grow very nice interfaces with these types of materials using deposition techniques like MBE. Interdiffusion and interface disorder is almost impossible to avoid. And this is a problem for trying to get strong exchange coupling between a surface state and a magnet, because any kind of disorder will push the topological surface state toward the bulk and away from an external magnet. The exchange interaction is sort of exponentially sensitive to that, and so you lose quickly if you start having disorder. So our thought is, well, can we do better by mechanical stacking of exfoliated letters rather than by using MB kinds of materials, with the goal of having really pristine interfaces with no intermixing? Okay, so that's what we've done. To start with, we use very high quality quaternary topological insulator materials grown by the Taylor Sparks group of the University of Utah. So bismuth, antimony, tellurium, selenium-2. And we've done these experiments with flakes of different quality, and you really need very high quality topology to start with to see sort of high temperature scales. The signatures of having a very high quality crystal are a sharp Dirac peak, just measuring the topological insulator flake by itself with no magnet, and then being able to gate through the Dirac point and seeing the ambipolar charge conductivity. So well-defined hole and electron transport on both sides of the Dirac. With these flakes, you can also, even before you put magnets on, look at the longitudinal resistance function of temperature, and they're dominated by the surface states below about 50 or 60 Kelvin. And these very high quality topologies will put us in a somewhat different regime than what's been done previously with the magnetically doped topological insulators, and that we have mobilities about 100 times more than the epitaxial magnetically doped samples with the topologicals by themselves. And even once we add the magnets, we're seeing mobilities, 10 times what's been measured before with the magnetically doped topological insulators. Okay, so we can get right to it. Now we want to combine these topological insulators with magnets. The structure is a gated structure with encapsulation by HBN. So we have an HBN bottom layer, the topological insulator flake, the chrome germanium telluride above it, and then we can put a gate electrode on top as well. The tricky thing about these studies was developing fabrication techniques to make well-defined Hall bars for measuring longitudinal and Hall conductance accurately without messing up the somewhat delicate materials. But we have good protocols for that. And at the bottom left here now, we sort of typical device where we do have a well-defined Hall bar. So the measurements are then simple. You want to measure the longitudinal and Hall resistance. On the left here, I show the Hall resistance. Now, instead of a 0.1 ohm sort of Hall resistance, the typical scale is about a 1 kilo ohm. And we also see very nice sort of butterfly characteristics on the longitudinal conductivity with minimum resistance corresponding to topological edge states along magnetic domain walls as the magnets undergo reversal. Okay, so we can then take these measured resistances and Hall resistances and convert them to conductivities and see what we see. So you just use the standard sort of technique, standard formulas for inverting the 2x2 resistivity matrix to determine conductivities. On the left here, I show measurements of resistance on one of these devices as a function of gate voltage. And if you convert those values to conductivities, what you see is on the right. So over a range of gate voltage around the drag point, you see Hall conductivities very close to 1/2 E squared over H. Not exactly 1/2 E squared over H, but that's to be expected in these devices because the longitudinal conductivity is not zero, as in sort of a turn insulator state or a two-dimensional electron gas in a high magnetic field. The longitudinal conductivity due to the bottom layer that's ungapped is still here, 6 or 7 E squared over H. So if there's any current inhomogeneities or any offsets, accidental offsets in the Hall probes, you'll get a small change in the Hall conductivity because of those events. But we see Hall conductivities of about 0.51, so within a couple percent of an exactly quantized value. And this is not a very low temperature here, even this is just at 4.2 degrees. Okay, so really you want to understand what's going on in detail here, you want to think about what is the temperature dependence. And it's also possible, as I'll talk about on the next slide, to make direct measurements of the strength of the exchange gap using capacitive technique. Here I show what goes on with the Hall conductivity as a function of temperature for gating near the middle of the exchange gap. We do see some temperature dependence, but it really kicks in above 10 Kelvin or so. The blue curve here shows the temperature dependence that would be expected if the exchange gap itself did not depend on temperature. And doing a rough fit to the start of the temperature dependence here at low temperatures gives a lower bound on the exchange gap, about 4.5 millielectron volts. But we don't believe that's the value of the low temperature exchange gap either, because as we see over this temperature range, it looks like the exchange gap itself is decreasing as a function of temperature as we go up in temperature, and that's essentially to be expected. We see reasonably large values of Hall conductivity all the way up to near the Curie temperature of the chrome germanium telluride, which is 50 or 60 Kelvin. So we can make more accurate measurements of what the exchange gap is using a capacitive technique that's been used before for sort of bilayer graphene and also previously by Vala Fatemi in the Herrero group for measuring the gaps in topological insulators at high magnetic field. The idea here is to use the bottom surface, the ungapped surface of the topological insulator as a sensor to measure the screening of a gate voltage by the top surface. The bottom surface still has a reasonable well-defined Dirac peak in the resistance. And so if you monitor the voltage required to stay at that Dirac peak, as you apply a top gate voltage, you can measure the screening of the top surface and thereby measure both the chemical potential and the charge density and that top surface. So this simple algebra about how this works, but to make a long story short, with these devices, I can measure the chemical potential as a function of carrier density in that top surface. And at near the drop point, you do see a jump that corresponds to a jump in about 10.2 millielectron volts. So that high voltage scale corresponds well to the temperature we see for where the quantization of the Hall conductivity remains. And just to compare to other structures, this is a much larger gap compared to thermal activation measurements of the longitudinal conductance in magnetically doped systems. Those are down below 0.1 millielectron volts. And even for manganese bismuth telluride, those kinds of measurements are down below 1 millielectron volt. And I think what's going on with that comparison is these are just really measuring different quantities. In those systems, those gaps are really determined by disorder and fluctuations in the potential. Here, we have much lower disorder in these pristine states. So we really do have more of a direct measurement of what the exchange gap looks like. Okay. So that's where things stand right now. It really does look like these sort of pristine interfaces that we can make by mechanical stacking make a big difference in the strength of exchange coupling, the proximity coupling between a 3D topological layer and a magnet. We haven't yet managed to put magnets on both sides of a topological lake. That's what we're working on now. That's been tricky mostly just because sort of growing these very high quality topological layers is a little bit hit and miss. And so some of our most recent crystals have been lower quality than the best ones we've dealt with. But we're working on optimizing the growth properties of these topological layers and be able to do this more reproducibly. We've seen these very high temperature scales and I think 3 different devices so far. With that caveat, we're working on making magnet layers both above and below, and working to investigate both the turn insulator state and the axion insulator state that come about once we have magnets on both sides. So so far I've talked about the effects of the magnet on the topological insulator surface state. There's also some interesting predictions that in the same system, there should be interesting effects on the magnet given by the topological state, so the other way. And the idea here is sort of a simple idea that you expect the magnet to have different effects on the surface state depending on whether the magnet points in plane or out of plane. And this gives an effect on the magnetic anisotropy. The idea here is if you have an in-plane magnet interact with the topological surface state, you don't gap the surface state, so you still have the Dirac dispersion. Whereas with the perpendicular magnet, as I mentioned, you expect to gap the surface state. What this means is if you have a Fermi level near the gap, the overall system energy can be lowered because the electronic energy is lowered if you have a perpendicular magnet compared to an in-plane magnet. So this interaction should give an effect contributing to the magnetic anisotropy, favoring an out-of-plane orientation rather than in-plane orientation. So we've looked for that as well, and things are a little bit confusing about that. If you just measure the hysteresis curve for a magnet, say this chrome germanium telluride magnet on the topological insulator versus just on a silicon wafer, there is a larger coercive field and a much more square hysteresis curve for the magnet on the topological insulator, which would seem to indicate that the topological does help favor a perpendicular magnetic anisotropy. However, if you actually measure the gate dependence of the coercive field, you actually see opposite what you expect. That the coercive fields have a minimum near the Dirac point rather than a maximum near the Dirac point. So we're still trying to figure out exactly what's going on there. But we think the picture must be a bit more complicated than the simple picture I showed you on the previous slide. Coming down to the fact that when you measure a coercive field, you're not actually measuring the anisotropy directly, but you're measuring a competition between the Zeeman energy from the magnetic field fighting against any anisotropy field. And it's also known with these magnetic topological samples that the magnetization of the surface state also varies depending on whether the magnet itself is in plane or out of plane. You have kind of a hedgehog magnetic topological structure of the surface state with that interaction. So our current theory is that the coercive field does not change directly proportional to the anisotropy because the Zeeman energy is also dependent on the magnetic anisotropy because of the spin structure within the topological surface state. So if there's people interested in sort of thinking more about that, we're still kind of puzzled about this, but yeah, this is something we are finding very interesting. Okay. So that pretty much completes the first part of the talk. I now want to sort of switch subjects and talk about something else that can be done with van der Waals magnetic materials. And this is trying to develop ways of probing and manipulating the antiferromagnetic dynamics in van der Waals antiferromagnets in a very direct way. So can we make something useful out of antiferromagnetic dynamics? To do that, what you need is to be able to test the dynamics directly in the time or frequency domain using microscopic samples, and then develop ways to ability to manipulate these dynamics electrically. And one potential goal I have in mind that we haven't quite achieved yet, but a goal to look for is to try to make, say, a high frequency nanoscale oscillator where you put in a DC current and sort of get out oscillations at the antiferromagnetic resonance frequency. So this is a challenge. What's been done previously with measuring antiferromagnetic dynamics has mostly been with very large samples, millimeter or larger samples. There have been nice studies about resonant absorption and spin pumping, able to measure sort of antiferromagnetic resonances with those techniques. And there's also been nice optical experiments on smaller samples using optical probes of MOC to measure the dynamics. But nobody sort of made much progress on making more practical devices operating at the high frequency scales of the dynamics. So our idea is to use a sort of a simple idea that's very similar to devices that have been made previously with some of the chrome triiodide related antiferromagnets, is just to use tunnel junctions and use spin filter tunneling through the tunnel junctions to detect not just the relative orientations of the spin subglass in the antiferromagnet, but also their dynamics. And so this builds on very nice work by Klein et al. And also Song et al., who studied these kinds of spin filter tunneling devices in the low frequency domain, where they're able to see switching between parallel and antiparallel alignment. But we now want to do this in the high frequency domain, looking at the dynamics. Okay, so that involves some microwave technology. Essentially, you want to develop things, minimize nonlinearities and sort of minimize impedances to try to be able to get microwaves in or out of these devices. So we've had to change the structure a little bit. But to do this, we've focused on the antiferromagnetic chrome sulfur bromide. This is an A-type antiferromagnet with in-plane magnetic anisotropy, where each layer is aligned antiparallel to each other at zero magnetic field. And this is a nice antiferromagnet for our studies because unlike chrome triiodide and other structures, it has biaxial anisotropy, so it has a well-defined in-plane axis that allows us to control the directions of the moments a bit more easily than with the chrome triiodide, which has very weak in-plane anisotropy. So to get started with these studies, rather than just losing ourselves in parameter space, we made some resonant absorption experiments to understand where the dynamics in these devices should be. So following McNeil et al. Experiments from Pablo's group. These are simple experiments in which you just take a coplanar waveguide, put a crystal of the chrome sulfur bromide on top, and then measure the microwave absorption as a function of magnetic field and frequency. So with these kinds of techniques, we're able to map out the nature of the dynamics in these structures as a function of magnetic field in various directions. Depending on the direction of the magnetic field, you do see different kinds of resonant modes. This structure this shows the kind of frequencies you see for an external magnetic field parallel to the in-plane easy axis. The dynamics here correspond to superpositions of right and left circularly polarized modes. Because of the magnetic anisotropy, these modes are coupled. So there is a non-zero gap, zero magnetic field. But you can understand the magnetic field dependence as a coupling of these two types of modes. As you go up the magnetic field, there's a narrow region of spin flop transition and then a transition to a fully parallel alignment of the magnetic axis above about 0.3 Tesla or so. If you look in other directions of the magnetic field, say here perpendicular to the easy axis, you see other types of modes. Here you have more of an acoustic mode and an optical mode with well-defined magnetic field dependence you can understand. By symmetry, there is no coupling between these modes if you have magnetic field perpendicular to the easy axis, and so there's no avoided crossing within this geometry. But if you have other magnetic fields, there is coupling. You can start to see avoided crossing. Anyway, the basic message of these sets of experiments is we do understand the modes. We can understand the various parameters governing what these modes are, the anisotropy parameters and the exchange parameters, and understand where to look for the modes as we make smaller scale devices. Okay, so to try to do the electrical readout on smaller scale devices, this is the nature of the devices we'll look at. There are 3 terminal tunnel junctions. On the bottom, there's a bottom electrode that for purposes of applying spin orbit torque, we use platinum telluride, which has a large spin Hall conductivity comparable to platinum itself. We have then a chrome sulfur bromide flake of a bilayer chrome sulfur bromide on top of that, and just a graphite top contact. So we can pass current underneath the device, apply spin orbit torque, and measure tunneling current going through the device, and measure the tunnel magnetic resistance. As a function of magnetic field applied either parallel or perpendicular to the nail axis, we can see easy or hard axis behavior and understand sort of the nature of the DC magnetic resistance here. So it's not a huge magnetic resistance, but healthy enough to be able to measure the dynamic. Okay. So to probe the dynamics, we use a variation of the spin torque ferromagnetic resonance technique. We apply an RF current through the bottom channel that can excite magnetic dynamics in the interferometer via both an Ørsted field and possibly from spin orbit torque. And then we measure the dynamics by probing the DC resistance through the tunnel junction. It happens there's some leakage of the RF current through the tunnel junction. So if there are any dynamics of the antiferrometer, the same frequency of the driving frequency, there'll be mixing between that AC current and the AC resistance that gives you both a DC voltage and a voltage at twice the drive frequency. And just by measuring the DC voltage and sweeping magnetic field at fixed frequency, you can map out what the modes look like. And so on the right here, I just show what this DC mixing voltage is as a function of magnetic field at several different frequencies of the excitation. You can see dips here at both positive and negative field that correspond to these resonances. You can map out what the resonance look like as a function of frequency and magnetic field on these sorts of color or black and white color diagrams. You see only one mode in these devices. You see the optical mode, but that's what you expect because that's the mode that has large angular changes between the spin sublattices that give you a change in resistance within the device. Within the device parameters we have, the acoustic mode would be along the dashed line here. We don't see anything. So first of all, from these measurements, you can work out what are the parameters governing the dynamics of the modes. You can work out what are the anisotropy and exchange fields within this bilayer device. And you can compare to bulk. The anisotropies aren't too different between the bilayer and the bulk. That's probably what you expect. But the exchange interaction is quite a bit weaker within the bilayer compared to the bulk samples we measured previously. Part of this is just within the bilayer, each sublattice only interacts with one sublattice on one side rather than sublattices on both sides. So it's natural that the exchange interaction is weaker. There might also be some charge exchange with the electrodes that changes the magnetic properties a little bit more than that too. Okay, so the bottom line is here that we are able to electrically detect the resonances on small micron scale structures rather than millimeter scale structures with this technique. We can then go on also and see if it's possible to start to try to control the resonances using electrically signals as well. And the way we want to do that is a first experiment, just see if we can control the line width of the resonance with spin transfer torque coming from current in this platinum telluride channel underneath the chrome sulfur bromide. And so our thinking here is an analogy with what's been done previously using spin torque modulation of ferromagnetic resonance within ferromagnetic thin films. And the idea here is kind of shown in this diagram. If you can change the line width of a magnet by passing a spin orbit torque so that you can apply a torque either parallel or perpendicular to the precession axis of a magnet. So in this diagram, you can think about if the sort of effective field is vertical here, if you have some magnet precessing along that effective field, there'll be some damping forces intrinsically that eventually cause that precessional motion to spiral and come to rest along the effective field. If you have a spin transfer vector, in this case, anti-parallel to the effective field, as the magnetization precesses around, there'll be a component of that spin transfer vector that points opposite to the natural damping at every point along the precession axis. So with this orientation of the spin transfer vector, you can essentially add some anti-damping that reduces the natural damping and causes the FMR line width to decrease. Whereas if you reverse the sign of the current, so as to reverse the direction of the spin transfer vector, you would get the spin transfer vector parallel to the damping force, give more damping, and give an increased line width in a ferromagnetic resonance measurement. And this has been measured very frequently now for conventional ferromagnets. And I've just taken data from a nice paper by Sophie Pettit here from 17 years ago now. But with ferromagnets, you can see as a function of one sign of current, you can see that the line width will decrease. And if you apply the opposite sign of current, you can get the line width increase. And this is due to a change in the effective damping due to a damping-like spin orbit torque coming from a spin transfer vector. So we want to see if we can do something similar to the resonances in our chrome sulfur bromide. So we'll look at very similar devices what I've talked about previously, with one bit of change here that we were clever with what we did with the direction of the nail vector. So with these devices, we align the nail vector of the chrome sulfur bromide at a 45-degree angle relative to the channel. And we applied a magnetic field 90 degrees to the nail vector along the hard axis to control the offset angle between the spin sublattices. And what we see here, we see different changes in the line width as a function of current depending on what direction we apply the magnetic field. So for one direction of magnetic field, I'll say that pointing to the upper right here, we do see a change in the line width as a function of current. So for say -3 milliamps, we see a smaller line width than for +3 milliamps. Whereas if we apply the magnetic field in the opposite direction, along the lower left here, essentially there's no effect of the line, there's no effect of the current on the line. So initially that was a little bit puzzling compared to the ferromagnets, where depending on the ferromagnets, you just change what sign of current is needed to change the line width. But it can be understood in a simple way by thinking about what's happening to the spin sublattices in these different orientations. So the data here corresponding on the left-hand side correspond to a magnetic field oriented such that the one sublattice is oriented, well, so there's about a 90-degree offset between the two spin sublattices, with one of them oriented perpendicular to the current direction and one of them oriented parallel to the current direction. And our understanding of what's going on for this orientation is if the spin sublattice adjacent to the platinum telluride channel is perpendicular to the current, that means that spin sublattice is parallel to the spin torque coming from this platinum telluride, which means it would be affected by the anti-damping torque. So what's going on with the opposite direction of magnetic field is for this orientation, again, you have a 90-degree orientation between the spin sublattices, but in this case, the spin sublattice adjacent to the platinum telluride is parallel to the current, while the spin sublattice at the other layer is the one that's that's perpendicular to the current. That means since the spin from the spin orbit torque is perpendicular to the current, the spin sublattice adjacent to the platinum telluride essentially doesn't have the benefit of the anti-damping torque. So the picture is here that really only the spin sublattice adjacent to the spin orbit channel is the one that is affected by the spin orbit torque. The second spin sublattice just doesn't see that. And so if that spin sublattice is oriented, if the second spin sublattice is oriented favorably relative to the spin orbit torque, it really doesn't get the advantage of that anti-damping torque. So the bottom line here is that if you think about what the change in the line width is as a function of DC current, for one orientation of magnetic field, you essentially see nothing. For the other orientation, you see a strong dependence of the line width on the current from the anti-damping torque. Now, within this picture, if you can reverse the direction of the nail vector, you should expect that also reverse what sign of magnetic field gives you a strong dependence of the line width on current. And in fact, that is possible to do. There's a little bit of asymmetry in the magnetization of the two layers. And so by applying a large magnetic field parallel to the nail vector or anti-parallel to the nail vector, you can reverse the nail vector. And when we do that, we do reverse the sign of the magnetic field that gives us a strong dependence of the line width on current. And that's just because by reversing the spin sublattice, we've reversed the sign of the magnetic field that aligns that first spin sublattice with the spin over torque direction. Okay. So as a function of the magnitude of the magnetic field, you can vary the offset angle between the spin sublattices and actually check to what extent the angular dependence agrees with the simple pictures you expect from the ferromagnetism. If we do that, plotting the sensitivity of the line width to current as a function of the angle of that first spin sublattice relative to the current, we see a nice cosine theta dependence that is what you expect is if all the spin torque is acting on just that first spin sublattice and not the spin sublattice in the second layer. And so with this, there seems to be no dependence on the angle of the second layer as to the strength of the anti-damping torque here. So our conclusion is really that the anti-damping torque acting on this antiferromagnet is very local, acting only significantly on one spin sublattice and not penetrating through to the second layer to affect the second spin sublattice. Okay. So one last comment just about how much we can actually modulate things. One of our overall goals here is to modulate the damping a lot to actually tune the effective damping all the way to 0 or to negative values. That would allow us to make antiferromagnetic nano-oscillators where a DC current would destabilize the dynamics and actually allow the antiferromagnet to start self-oscillating. Within our original generation of devices with the platinum telluride, we can only reduce the line width by about 12% before heating started to take over and the line width would start to go back up as we went up to higher magnitudes of negative current here. We've continued to work on that with improvements both in the device geometry and trying out some different spin orbit torque materials. Our best result from last week now is that we can actually modulate the line width by at least 85% before heating kicks in. And this may already be enough to get close to where we'll be able to start to see some self-oscillations. So we're beginning those measurements, and hopefully I'll have more to report to you within the next few months about that. Okay, so that's the stories I wanted to tell. So just to summarize the two parts and to give some credit to who actually did the work, I've shown that by using exfoliation and mechanical assembly to make heterostructures between 3D topological insulator and an insulating magnet, we can achieve much stronger exchange gaps than what's been done previously through MBE grown structures, and achieve a quantized anomalous Hall effect, a half quantized anomalous Hall effect in the parity anomaly regime at temperatures up to greater than 10 Kelvin. We haven't yet coupled magnets to both sides of the topology to have a fully quantized state with dissipation edge channels, but at least for the magnetically doped topologies, those states and the parity anomaly state have the same temperature scale. And we're very optimistic that with some improved device fabrication, we'll be able to see those kinds of physics too. And then second, working with the dynamics of van der Waals antiferromagnets, we've developed techniques to directly measure in the frequency domain these antiferromagnetic resonant modes and begin to be able to manipulate them with spin orbit torque within one unified device. The students who've done this work were for the quantized anomalous Hall effect studies. They were initialized by Vishaka Gupta, and the current group members who are moving this forward are Rakshit Jain and Matt Roddy. With the antiferromagnetic dynamics, that was done by Talman Cham and Kelly Lowe, and Rakshit Jain has also been contributing to some of those recent experiments. So this is where I'll stop, and happy to have discussion and questions.
Great. Well, thank you, Dan. That was fantastic work. For those of you who want to ask questions, raise your hands, and I will be promoting you to the panelists. I seen already Matthias who wants to go ahead and ask the first question.
Yeah, thanks, Dan. Really exciting results. I have a question about the heterostructure where you showed this topological insulator in contact with a ferromagnet. Now, do the results change upon multiple heating and cooling cycle? So when you just heat the device to room temperature and cool it back down, does it change? Because we've seen that the van der Waals gap can change as you heat and cool due to different thermal expansion coefficients.
Yeah, so we've noticed that the coercivity and the remnants changes a little bit upon repeated heating and cooling. That if you look very carefully, some of our experiments show a well quantized remnant state, and some of them begin to curve down a little bit once we get exactly to zero magnetic field. But that's the biggest change we've noticed from the cycling.
Okay.
We haven't noticed big changes in the exchange gap. Sometimes the devices don't survive repeated cooling and cycling, but when they survive it, they don't seem to change much in terms of the magnitude of the gap.
And does the angle matter under which you stack?
So that's not something we've understood how to control very well. This is not a tear and stack kind of thing where we have a well-defined relative orientation between the layers. These are different materials.
Yeah. You cannot see easily from the shape of the flake which crystallographic orientation you're on.
Not to my understanding.
All right, great, thanks.
Mm-hmm. Very good. Helen, would you like to? Yeah, go ahead, Helen. You have to unmute yourself. Yeah, you're muted.
Very interesting talk. I have more questions to the second part related with the dynamics of antiferromagnets. So you showed the numbers of the exchange fields, and they're extremely small. They are smaller than anisotropy.
Right.
Yeah. So then the question. Is it important for your experiments? So your sublattices are almost disentangled, so the coupling is very small. So if you will go to the higher values of the exchange field, would you be able still distinguish between these effects, between two sublattices?
So I think the hard part would be as you go to larger exchange couplings, you just get to higher and higher frequencies. And technically the experiments get more difficult that way, where you have to worry about roll-offs and sort of resistance, the timescales of the by which you just can't get the microwaves in and out of the devices anymore. So these experiments are definitely easier for the van der Waals antiferromagnets, where the exchange coupling between the layers is reduced because it is van der Waals, compared to a 3D antiferromagnet where they might have hundreds of gigahertz or terahertz frequencies. But I think that's it's that technical issue rather than something fundamental that would make things difficult.
The frequency is not so big issue because the frequency depends on the product of course, if we are talking about the lower frequency mode, but if you increase exchange and lower anisotropy, you get the same. For example, in hematite, you can get 10 gigahertz for the lowest mode, so okay. It's not a big issue.
Yeah. So I think you might be able to do something similar there. I think having a layered antiferromagnet is probably, I'm not sure what would happen to the spin filter tunneling if you didn't have separate layers. So hematite might be more tricky that way. But we haven't done anything other than the chrome sulfur bromide ourselves at this stage.
If there's questions, please raise your hands, because otherwise I cannot guess. But I'm going to ask you a question. So in the first part at the end, when you showed this reduction of the coercivity effect, can you show that again?
Right. You want me to show it again? Yeah.
Yeah. Wanted to understand a little bit of what the observation is. So it wasn't a little bit fast for me to think about it.
Okay, let me just stop sharing for a second and then go back.
again, all of the anybody that wants to ask, raise your hand so I can give you the floor to ask a question directly to them, or write it on the chat. There's 120 of you, so it couldn't be all of you. Yes, it was so clear. Oh, that's good reason. Okay. Yeah, so there.
Okay.
Very good. So in here, you're seeing that. So this is a system. So the coercivity now goes way down. For which this is the part I didn't understand between the top and the bottom of those two devices.
Yeah, so these are just the coercive fields for positive magnetic field and negative magnetic field.
Okay.
So the magnitude goes down in both cases.
In both cases. And these are the systems where they just, I guess your idea is here that the anisotropy or the anisotropic field, effective field, is overcoming degrading the coercive field itself. Yeah.
So if you think about what determines the coercive field, there's what is the influence of the magnetic field trying to drive the magnetization parallel to magnetic field versus the anisotropy field trying to oppose that. Mm-hmm. And our thought is what might be going on here is that as you tune the gate voltage through the exchange gap, you're changing what the magnetization of the surface state is, as well as changing what the anisotropy of the magnetic layer is.
Yes, but are you looking at only the out of plane field?
Yeah, so this is just
or is the anisotropy now changing and being in plane? So the coercive field maybe that one is down, or not. So
the experiments we've done are with out of plane fields so far. With in-plane field, things are a little bit trickier trying to measure anisotropies that way, just because you're close to a quantized value of the Hall resistance. And so the normal way to measure that would be to sort of apply magnetic field, have the magnetization tilt, and measure the tilt from the change in the Hall resistance. But if the Hall resistance isn't changing as a function of tilt, you can't tell what the anisotropy is that way.
Very good. That's interesting result. Shahid Sattar, can you go ahead and ask your question? You can.
Yes, thanks a lot for giving me the floor. I wanted to ask about the origin of non-zero longitudinal conductivity. Mm-hmm. And regarding that, you mentioned that it is because of the ungapped bottom surface. Do you think there might be other reasons for that?
So I don't know. I mean, there is a large conductivity coming from that ungapped surface. So it's hard to know what other contributions there might be as well. I think that's really all I can say.
Oh, okay. And the second thing in connection to that, do you think that there can be some nonlinear contributions that can be the reason for that? And do you consider that in measuring these conductivities?
So that's a very good point. Very interesting question. We've spent a little time looking at that, but not a whole lot. We haven't noticed anything exciting along those lines, but I wouldn't rule out that there could be effects along those lines. We haven't studied that carefully yet.
Okay. If you don't mind asking one last question. So you looked at the effects when you consider chromium germanium telluride. Have you also looked at other ferromagnets like chromium iodine? You mentioned about that there is an exchange gap. Have you performed any experiment?
We haven't tried those yet. Chromium, we've tried chromium a little bit. That's trickier just because it's a lot more air sensitive. And even if you have things well encapsulated, things can go wrong with chromium triiodide. So we don't have anything to report about that yet.
Okay, thank you so much.
Hanboom Park, go ahead and take the question.
Okay, hello, Ralph. I have a question about the second part. So in your sample, you made the sample with the nil vectors tilted with the current direction. So have you tried the nil vectors parallel and perpendicular to the current direction?
We have done some of those too. They weren't all that much qualitatively different compared to what we expected based on the resonant absorption measurements. But having things tilted just gives us a bit more control about controlling the relative orientation and being able to see large effects. You essentially want to be near 90-degree misalignment to see the largest resistance changes too. So that's part of what we choose the orientations here.
Okay, so the 90 degrees and can enhance the signal, so that's why you intentionally make.
Yeah, so we almost always have a magnetic field bias to give us sort of a close to a 90-degree offset to be able to see large signals.
Okay, I see.
And the last question is from Ali Reza.
Thank you.
So he asked, then from the first part of the talk, is there any signs of tunneling between top and bottom layers in the thin films of the topological insulator? Is there any thickness dependency on the experiment?
So we haven't looked in detail at thinner layers. We picked layers, I think the topology is always more than 5 quintuple layers, just to try to make sure that we don't have trivial gaps from that sort of coupling. But again, we haven't done a huge amount of thickness dependent studies yet. Okay,
good. So I think those are all the questions. I'm going to stop the streaming now. The streaming.
There is one more question, I think.
No,
No, it popped out in Q&A.